Okay, during our rounds, one of the last things we looked at was a bunch of division problems where we divided by a linear polynomial whose coefficient was 1. And we discovered that when you do that division, the remainder upon that division is the same as the value of p of c. Okay, so let's review that real quick. Okay, we started with a polynomial, p of x, and we were asked to do the division x minus c. Now we've been putting the answers in the form q of x for quotient plus remainder of x divided by the divisor, which in this case is x minus c. One of the things we observe is when you divide by a linear polynomial, you're always going to get the remainder to be a constant because x will go into all powers of x except a constant power of x. So this x will go into any power of x cubed, x squared, x to the first, etc. Okay, so what ends up happening is when you divide by a linear polynomial, your remainder ends up being a constant. Let's call that constant k. Now if you multiply both sides of this equation by x minus c, you would get p of x, because the x minus c's cancel on the left-hand side here. You would get q of x times x minus c. And then the x minus c would cancel on this term and be left with a plus k. Now if you insert a c for x, this is going to become 0 because c minus c is 0, and you're left with k. Okay, so that's a real quick proof of that statement. Now, that's kind of interesting in itself, but then there's a bigger question that we want to look at. That question is, okay, what if we do long division and the remainder is 0? Okay, that's possible. That could happen. So let's take a look and see what would be the case there. Okay, so if we take a polynomial p of x, we divide it by x minus c, we know we're going to get a polynomial called q of x plus my remainder, which is 0, divided by x minus c. This term over here is 0, so I don't have to worry about it. So I have p of x over x minus c is equal to q of x. And I'm going to do the same idea as I'm going to multiply both sides by x minus c. Now, I look at this and I observe a couple things. Since there's nothing over here, x minus c is now a factor of p of x. So that's one thing I get from the remainder being 0. Okay, x minus c is a factor, or I could call it a root, of p of x. And if we plug c in for x, we're going to notice that p of c equals 0, which means c is a 0 of p of x. So what this ends up telling us is that long division, if it gives us a remainder of 0, can help us find the roots or the zeros of a polynomial, which is convenient for solving equations and also for graphing. What that means for us today is we can now go past the levels on the factoring pyramid that we gave you on the first day of class and now get the final level of factoring, okay, which has been labeled PQ, kind of mysterious name for a factoring method, and now we're going to learn what that means right here. Okay, so this is called the rational root theorem. It's kind of wordy, but it's very useful for finishing off the factoring pyramid here. Here's what it says. It says if a polynomial, which we know what a polynomial now is, has integer coefficients. So remember, integers are positive and negative whole numbers. So -7, 6, 0, 5 are integers, okay? 1/2 is not an integer, square root is not an integer, etc. So if your polynomial has integer coefficients, then every rational 0. So we're talking about numbers that are rational numbers which means they can be written as a fraction of two integers. Okay, and these numbers are going to make our polynomial equal to 0, the zeros. So every rational zero that the polynomial has to have this form, p divided by q. What are p and q? Okay, p is a factor of the constant coefficient. So that's the coefficient that has no x's attached to it. And q is a factor of the leading coefficient. So that's the coefficient of the highest power of x in your polynomial. So let's take a look at a quick example. We're not going to factor this one, but just what this theorem is saying here. Okay. So if I have a polynomial, and let's say my polynomial is 10x cubed plus 4x squared minus 6x minus 20. Eventually we're going to be asked to factor this, if possible. And to factor this, I'm going to do long divisions to try to find zeros, to figure out when does the remainder end up being 0. Now I can go ahead and try to test all sorts of numbers, but I might be here a while because there are lots of numbers to test. This theorem says that if this polynomial has rational zeros, okay, it might have irrational zeros, so I can't account for those. But if this has rational zeros, then they have to be of this form p over q. So this limits my possibilities and gives me a checklist to go through. So p has to be a factor of the constant coefficient, which is negative 20. So the factors of negative 20 are plus or minus 1, 2, 4, 5, 10, and 20. Divided by, okay, q is the factors of the leading coefficient, which is 10. So those factors are plus or minus 1, 2, 5, and 10. So combinations of these numbers are the numbers I would test until I get into a remainder of 0, and I'll have a factor or 0 of the polynomial. So I'd have to test positive negative 1, positive negative 1/2, positive negative 1/5, positive negative 1/10, etc., until I find a winner. Now this might seem like a big list and a lot to do, but you got to remember, you're limiting your choices to a small number compared with the infinite number that there could be. So this has its usefulness, and you'll come to appreciate it as we go. So let's jump into an example. Okay, here's my polynomial p of x. It's a 6th-degree polynomial. It's huge. I want to factor it. Okay, why? In this case, maybe to graph it. But we're going to see in this example the usefulness of the rational root theorem. Okay, so I'm going to try long division, and in this case it's going to be synthetic division, but I need to know what numbers are possible to test. I need a list. Okay, so what are my choices here that are possible rational zeros? Okay, the factors of 12, which are plus or minus 1, 2, 3, 4, 6, and 12, divided by the factors of 2, which are plus or minus 1 and 2. Okay, so that's a substantial list, but it's not impossible to go through and test those sets of numbers here. So what I would recommend you do first is, if you can in your head, test 1 without doing any long division. Okay, so I'm going to plug in 1 for x and see if I get 0 as an answer. If I do, then I'm glad, because I've just made my problem simpler. So I'm going to mentally plug in 1. I get 2 minus 3, that's negative 1, minus 13, that's negative 14, plus 29, that's 15, minus 27, that's negative 12, plus 32, that's 20, minus 12, which is 8. So 1 is out. Okay, so I can say I've tried 1 and it didn't work. Now I'm going to go into long divisions and see if I can come up with a remainder of 0, which will tell me that that number is a 0, which means I can then factor this into a smaller piece and then do it again. Okay, so the next easiest number to test is probably negative 1. So I'll put negative 1 on the shelf. And now I put the coefficients in order of descending power of x up here. And then we go through our synthetic division algorithm. Bring down the first number, multiply. Add those together, 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 multiply. Okay, and I don't really care what this number is. It's not 0. Okay, so that tells me that -1 is not one of the zeros of this polynomial. Okay, so -1 is now off my list. It's your choice where to go from there. I'm going to be kind of systematic and go kind of make the numbers increasingly bigger because multiplication is easier with smaller numbers. So let's try 2 next. Okay, so 2 is on the shelf. Same coefficients, 2, minus 3, minus 13, 29, minus 27, 32, and minus 12. Bring it down, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, multiply, and look, I got a remainder of 0. That's good news, okay? That means 2 is a 0. It also means that x minus 2 is a factor. Okay, so I can write p of x now as x minus 2 times, and remember what these numbers represented before, these are coefficients of the quotient. So I now have, let's start from the rear because that's easier to do, 6, negative 13x, 7x squared, negative 11x cubed, 1x to the 4th, and 2x to the 5th. So I've taken p of x, I have found one of the zeros, and now I've made the polynomial 5th degree, a little bit smaller. And now we've got to continue the process on this 5th degree polynomial. Same thing, I can't just factor it by looking at it, so I'm going to have to do some long divisions until I get a remainder of 0. Now, what are my possibilities for this polynomial right here to have rational roots? Well, they are the factors of 6, which are 1, 2, 3, and 6, divided by, let me write choices, okay, plus or minus 1 or 2, which are the factors of 2. Now, the good news is I can already eliminate 1 and -1 because I tested them up here on the original polynomial and they didn't work. So they're not going to work down here on this new polynomial. So I still have 1/2, -1/2, 2, 3, 6, 3/2, -3/2, etc. to test. Okay, so I'm going to go systematic again, and I'm going to test 2 once again, because 2 might divide the new polynomial. I don't know. Okay, so let's do 2 on my new polynomial. My coefficients are 2, 1, minus 11, it's a 7, minus 13, and 6. Okay, bring down the first, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. I got a remainder of 0 again. Okay, so I'm lucking out on this problem here to find the good ones early. Okay, so what does this mean? Okay, it means x minus 2 is a factor of this new polynomial. So that means x minus 2 is a double root, repeated root. So I could write it squared, but for now I'll just write it as x minus 2. So you can see that I'm bringing down this x minus 2 and now including a new x minus 2. And the resulting polynomial has these coefficients right here. So that's 2x to the 4th plus 5x cubed minus x squared plus 5x minus 3. Okay, now I'm at a 4th degree polynomial. It's getting smaller as we go. I still can't factor this just by looking at it or using older techniques. So I'm going to go ahead and do the rational root theorem one more time, or at least one more time, but at least on this new polynomial. All right, so let's jump to a new piece of paper. This is my 4th degree polynomial. Remember that there's still 2 factors, x minus 2, that are off to the side here. What are my possibilities, okay, to test? My possibilities are now plus or minus 1 and 3 divided by plus or minus 1 or 2. So the choices are dwindling now. I have 1, which I know is not correct, negative 1, which I know is not correct, positive 3 and negative 3, and then 1/2, negative 1/2, 3/2, and positive 3/2. So we're getting down to a few choices here. So let's test negative 3, I guess. Put that on the shelf. 2, 5, minus 1, 5, and minus 3 are the coefficients. Bring down the first, multiply, add, multiply, add, multiply, add, multiply, and I got a remainder of 0. So negative 3 is a 0, which means x plus 3 is a root. So going back to our original p of x, we had 2 factors of x minus 2. I'll now write that as squared. We can add a factor of x plus 3. And what's left is 2x cubed minus x squared plus 2x minus 1. And now I might be in a position to use one of my old factoring techniques. I'm down to 4 terms. So it's possible this might factor by grouping. So let's take a look. I can factor out an x squared from the first 2 terms and be left with 2x minus 1. And lo and behold, if I stick out 1 out in front, I have 1 times 2x minus 1 down there. Bring down my work so I don't lose track of it. So this factors by grouping as x squared plus 1 and 2x minus 1. And I still have my x minus 2 squared and my x plus 3. And there's my p of x. So I have now factored this as far as it will go. X squared plus 1 is the sum of 2 squares. It does not factor with real numbers. This would produce imaginary zeros, so we don't worry about those. But if I was going to graph this, I can tell you there's a 0 at 1/2. There's a 0 at negative 3. There's a 0 at 2. At 2, there's a point of tangency. The graph crosses through negative 3 and 1/2. If I go back to the original polynomial, I know the y-intercept is negative 12, and I know the end behavior is the end behavior of an even polynomial. So I can tell quite a bit about that original monster once I have it factored down into its DNA.